Welcome back. Today we're going to look at reviewing for our Chapter 7a test on exponential functions. Our first couple questions here, it says decide whether or not the listed function represents growth or decay, and then give the percent of growth or decay and identify your y-intercept. So first thing I look for is what's inside here being raised to the power. If it's 1 or higher, if it's higher than 1, if your base is bigger than 1, it's going to be growth. Okay? If you're between 0 and 1, it's going to decay. So in this case, we have a decay situation. And the percent that it's decaying, you're looking at how much below that 100% are you at. So if we have 0.7, which would be 70%, we're 30% below where we should be at to be at 100%. So we have decayed 30%. Okay? And then to find the y-intercept, we look at that front number. Whoops, not what I wanted to do. All right, to get our y-intercept, we're going to look at that front number. So since it's a 5, our y-intercept is 0, 5. Okay. The other thing you can do is you can put a 0 in for x, but 0.7 or anything to the 0 power is 1, which is going to get you back to having 1 times 5 be 5. Okay. For our next example, again, we're looking at that middle, that piece being raised to the power. Since it's bigger than a 1, we have a growth situation. And we are at 1.45, which would be 145%. That means we're 45% above normal. So we've grown 45%. Okay? Our y-intercept, again, is that very, very front number. So at time 0, when x is 0, we are having a y-coordinate of 0.4. All right. For question 3, be very careful. Notice that we have a negative power. And remember, with negative exponents, we have to flip. So this 5 that's being raised to a negative x is really the same as 1/5 to a positive x. So we're going to think of this equation as 14 times 1/5 to the x power. Now 1/5 is a number between 0 and 1, so we know it's a decay situation. We're at 1/5, so 1 minus what percent or what fraction would give us 1/5? We're going to have to subtract 4/5. Okay, 1 minus 4/5 would give us 1/5. So we have decayed 4/5. And 4/5 as a decimal is 0.8, which means we've decayed 80%. Our y-intercept, again, is the coordinates 0, comma, the first number there, the 14. All right. Looking at our next section, we are graphing these. It says describe how the graph of each function is related to the graph of its parent function, and then graph it and list the domain, range, and asymptote. So for my description, let's look at what's happening to this. Our base is a 3. It's being raised to the x power. So our parent function for this is y equals 3 to the x. Okay? What we're doing to it, with the negative that's in front, we are reflecting it over the x-axis. And then that plus 3 on the very far end means we've shifted it up 3. All right. Let's make a table of values for our parent function. All right. So 3 to the negative 2 power causes us to flip this. Let's actually start with our positive ones. It'll be easier. 3 to the second power gets us 9, which means 3 to the negative 2 would get us 1/9. It's got to flip over. 3 to the first power is 3. So 3 to the negative 1 is going to be 1/3. And anything to the 0 power gets us a 1. Okay? Now, we have to flip those over, and then we have to shift everything up 3. So you can add a third column here, and let's get the flip figured out. So y equals negative 3 to the x is going to cause all of these to just change sign. So the 1/9 will be negative 1/9, the 1/3 will be negative 1/3, the 1 becomes negative 1, 3 becomes negative 3, and 9 becomes negative 9. All right, sorry for that PA announcement interruption. So back to what we are looking at here. We are pairing these x's with these new y's. Okay? So at -2, we are at negative 1/9, which means we're just underneath the x-axis. At -1, we're at negative 1/3. 0 gets us negative 1. 1 got us to a negative 3. And 2 gets us to a negative 9. All right, so we have our exponential growth curve flipped over the x-axis, and now we have to move everything up 3. So my final position, moving everything up 3, will give me this red part. I do want to pay close attention to the asymptote because we need to know where that moved to. And any kind of up or down movement is going to move the asymptote. It used to be on the x-axis, but we're going to move everything up 3, so my asymptote is actually going to be right up here at y equals 3. And that means that my graph is going to come up and approach that line, but be right underneath it. Okay, so my domain is all real numbers. I can put in negatives, positives, decimals. I could put anything in for x. But my y values will not go above that green dotted line. So my y values are going to have to be less than that 3. Okay, let's look at another one. This time we have y equals 8 times 1/2 to the x power minus a 5. So again, analyzing our parent function would be y equals 1/2 to the x power, okay, getting rid of all the transformation parts. Okay, what we are doing to that, the 8 is going to cause it to have a vertical stretch of 8. The negative 5 on the end is going to shift it down 5. All right, so let's make a table of values. Remember, we start with -2 and go up to +2. Just looking at our parent function here, okay, y equals 1/2 to the x power. So 1/2 to the -2 power means we're going to flip that and square it. So flipping it turns it into a 2, squaring it turns it into a 4. 1/2 to the -1 power just is going to cause it to flip. Anything to the 0 power is 1. 1/2 to the first power is 1/2. And 1/2 to the second power, we square them both, we get 1/4. Okay? So I'm going to start out with my parent function points. -2, we're up at 4. -1, we're at 2. 0, 1. 1 1/2, and 2 1/4. Okay? Then we said we're going to stretch it. So let's get our stretch figured out here. 8 times 1/2 to the x. So we're going to take all our y values and multiply them by 8. 4 is going to turn into a 32. 2 is going to turn into a 16. 1 is going to turn into 8. Half of 8 is 4. And 1/4 of 8 is 2. All right. So let's move all of our points then. Let's see. -2, 32 is going to be way off my graph. Even 16 is way off my graph. But let's go ahead and start here at 0, 8, 1, 4, and 2, 2. Okay? Now, Our last piece is that we're going to shift everything down 5. And remember, if we go down 5, the asymptote moves as well. So our asymptote's going to move down here at -5. And we're going to take all those green dots and shift them down 5. All right, so my 8 is going to land at 3. 4 down 5 is going to be at -1. 2 down 5 puts me at -3. And I know that I'm curving down and approaching that horizontal asymptote. Again, we should be staying just above it. All right. So domain. Again, we can use any numbers for x. My range, though, all of my y values are going to have to stay above that purple line. So y has to be greater than -5. All right, one more graph. We have y equals 3 to the x minus 2 minus 1. Our parent function, ignore the transformations. We just have y equals 3 to the x. And we actually made this table of values for question 4. So using that same table, three to the second power is 9, which means 3 to the -2 is 1/9. 3 to the first is 3, so -1 would be 1/3. Anything to the 0 is 1. So 2, 9, 1, 3, 0, 1, -1, 1/3, and -2, 1/9. Okay? Now, for our transformations, we have an x minus 2, which means we have moved it right 2, and then the -1 on the end is going to shift it down 1. All right, so we're going to take all our dots and shift them right 2 and down 1. Okay, and then remember also that our asymptote shifts down as well. So our asymptote is down here at -1. And my graph is going to come down and approach that. Okay, domain, x equals all reals. Range, my y values are all above -1. All right, so that's the first part of our chapter. We looked at graphing exponential growth and decay curves. This would be an exponential growth curve. As we move to the right, our points are getting higher. And our previous question here, number 5, would have been exponential decay. All right, let's shift to some questions about exponential growth and decay, some word problem applications. It says, write an exponential function to model the situation and then solve it. So remember, if we're trying to just model, we're trying to make something a little more generic. We're not going to actually put the specific time in there. We're going to look at what would be kind of the trend for any time. It says kangaroo populations in Australia are said to be decreasing at a rate of 2.4% per year. Researchers this year found 14,000 kangaroos in the wild. How many would there be in 5 years? So again, we're going to hold off on this little piece for a minute and just get our basic formula set up, okay? So our population started out at 14,000. And you can use a Y, you can use an A for amount, P for population, it doesn't matter. 14,000, and what we're doing to it is, it says it's decreasing. So we want 1 minus our R value. And remember, all of our rates have to be converted into decimals from their percent form. So we move the decimal back to the left 2 places. This would be 0.024. And then we're going to have just an x or a t power. You can use a t. Might be a little easier to understand for time. Okay? Then it says to find how many there'd be in 5 years. So now we can actually plug the 5 in. 14,000 times 1 minus 0.024 to the 5th power. We're going to grab our calculators. So we have 14,000 times 1 minus 0.024 power 5. Okay, and we get that. Now remember, we're talking about the number of kangaroos, so we would want to round that to 12,399. All right. Question 8 says house values are on the rise. Your family invests in a $120,000 house because the realtor says the houses in that neighborhood are increasing in value at a rate of 4.5% per year. How much would our house be worth if we want to sell it in 4 years? So again, let's write our model first. Okay. Our total amount, again, you can use a Y or you can use an A, it doesn't matter. Our total amount is $120,000. We're multiplying that by 1 plus, because it's increasing, 4.5% would be 0.045 for our rate, and then to a generic time. Okay? Now we can do the specifics. How much would our house be worth in 4 years? So we can actually plug a 4 in for our time. All right, so this time we have 120,000 times 1 plus 0.045. Didn't take my decimal. And power is 4. So since we're talking about money, we would put this in as $143,102.23. All right. Question 9. Your starting wage at work is $8 per hour, and your boss says that you will receive a 6% bonus each year. When would you make over $10 per hour? So this is one that we're going to need to use a table to help us figure it out, because we're given a total amount, not a time period. Okay, so let's start out with our basic formula. We have $8. We are getting a bonus, so it's increasing. 6% would be 0.06, and we have some unknown time period. Okay, and we are trying to figure out when we're going to hit $10 for our total. So let's go to our table. We need an equation in here. We want 8 times 1 plus 0.06 and our power is going to just be our unknown x, and then we're going to go to our table, second graph, and look, we want to hit $10. Notice after 3 years we're only at 9.52 or 9.53. And after 4 years, we're at that 10.1. So it's going to take us 4 years to get to at least $10. Okay? So we said at 3 years, we were at about 9.5. At 4 years, we're at 10.1. So it's going to take 4 years. Okay? Question 10. From birth, your parents set up a bank account to help save money for your first car. They put in $4,000 with a 5% interest rate compounded quarterly. How much money would be in the account when you're 16 and you want to buy your first car? So it is important to pay attention to this little phrase here, compounded quarterly. That tells me I have to go to that bigger compounding interest formula. All right, so we need A equals P times 1 plus R divided by N to the NT power. All right, P is our principal, our starting amount. And they told us that we had $4,000. Okay, our interest rate, R, is 5%. As a decimal, we'd have 0.05. It's being compounded quarterly, so our N value is going to be 4. Quarterly means 4 times a year. And then our power is going to be 4t. Okay, that's our generic model. Now it says, how much would be in the account when we're 16? It told us they started this when we were first born, so our time here is going to be 16. So we need to take 4,000 times 1 plus 0.05 divided by 4 to the power 4 times 16. All right, again, let's grab our calculators. All right, we want 4,000 times 1 plus 0.05 divided by 4. And our power, we want to have 4 times 16. So again, some of you might need to use parentheses around that power to keep you up in that position. All right, so we will have about $8,800 to spend on our first car. $8,858.13 to be specific. All right, our last question. It says you put $1,500 into an account earning 2.5% compounded continuously. That's an important thing here. Compounded continuously. That tells me right away that I need to go to that other compound interest formula, my PERT formula. Okay? Find the amount in the account at the end of 7 years. So again, let's set up our model first. We have $1,500. That's my principal. And my rate that I'm getting for interest is 2.5%, which converted to a decimal would be 0.025. So I'm going to have 0.025t. That's my generic model. And now I want to actually figure out how much I'll have after 7 years. So 1,500 e to the power 0.025 times 7. All right, let's figure out what that is. 1,500 times e, so second, and then that ln key stands for natural log. Our power now is 0.025 times 7. So we will have $1,786.87. All right, so we started with $1,500. 7 years later, we've gained $287 roughly in just extra interest. All All right, so make sure you spend some time tonight reviewing for tomorrow's Chapter 7A test.